So this is part 5B of week 7. So far we have been limited to quadratic error functions that arise when we optimize the parameters for predicting the subthreshold potential. However, from a good neuron model, we also expect that we should be able to predict spike times. So here's an example. We have an experimental data set with current injection. An experimental data set contains spikes and it contains voltage traces. And so far we mainly focused on the subthreshold membrane potential. And the model in red does very nicely in comparison to the data. Now, if you want to predict spike times, we'll need also adaptation, and we will also need a dynamic threshold. Now, the two things are a little different. As I explained in the previous part of this lecture, there's a subthreshold membrane potential caused by adaptation currents. And these adaptation currents can be optimized by looking at the membrane potential, if we predict the membrane potential. However, if we also want to predict spike times, and at the same time the membrane potential, we have to separate the notion of a dynamic threshold from the notion of adaptation currents, or equivalently, spike after potentials. So here is our standard formulation with spike after potentials. The input is filtered with a filter kappa. Output spikes are generated stochastically. The feedback goes back as a contribution to the membrane potential, that adds in here, as well as a contribution to the dynamics of the threshold, that adds in here. And firing times are generated stochastically by the neuron model. And now the aim is to not just predict the subthreshold membrane potential, which we can do by optimizing kappa and eta using quadratic error functions on the membrane potential. Now we also want to predict the spike times. But predicting spike times involves this stochastic firing intensity, which is a nonlinear function of the voltage. And here is a very nice result. Note that the membrane potential, as discussed, is linear in the parameters eta and kappa. We have this dynamic threshold. The dynamic threshold is again linear given the spike train. The spike train has been measured. I've discussed before that given the spike train, predicting voltage is linear on the parameter. Given the spike train, optimizing the threshold is linear in the parameters theta 1. It's just a convolution. But we have the nonlinearity in the firing intensity. This function f is nonlinear. Now for the quadratic optimization problem, we always know that there's just a single minimum. If we have some arbitrary nonlinearities, in general we could arrive at situations where we have multiple minima. And if you just locally look for a minimum, you might get stuck in this local minimum, which is not the best one. Now it turns out that if we take for f an exponential function, as we should do, because it nicely fits data, if you put in an exponential function here, then the error function as a whole, is not of this form. It's a convex function, which has only one single minimum, which means we can use standard optimization procedures to go to the minimum. Convex means that if I put a connecting line between 2 points, it stays above the error function. So this case here is not convex, and this is also not convex. So how does this come about? Well, I have the membrane potential, linear parameters. I have the threshold, linear parameters. I have one single nonlinearity. Now, if I look at the log likelihood, then it's just the error function with the minus sign. So in fact, I just took the graphs on the previous slide and flipped them around. And so it's now finding a maximum rather than a minimum, if you plot here the log likelihood. And the result which I mentioned on the previous slide, which is due to Liam Paninsky, states that such a neuron model has a log likelihood function which is concave, which only has one single maximum. And that means parameters can be optimized in a systematic fashion by maximizing the log likelihood. In particular, the parameters of the threshold, which you still have to optimize, can be done in this systematic fashion. So in the procedure I discuss here, we optimize eta and kappa using the membrane potential. Then these are fixed, and we optimize theta so as to optimize the log likelihood of the spike times. With extracellular recordings where you don't have access to the subthreshold membrane potential, you can directly optimize log likelihood and find all three sets of parameter, theta 1, eta, and kappa. Let me summarize. In the procedure I've discussed here, if you have access to the subthreshold membrane potential, then we can optimize parameters of the filters kappa, the membrane filter, and of eta, the spike after potential, using a quadratic error function. The problem is linear in the parameters and therefore easy. If you want to predict spike times, then we can optimize the likelihood that the data spike train could have been generated by the model. And in this case, we have a problem that's concave, that has a single maximum as a function of the threshold parameters, the parameters of this filter theta 1. And again, this means it's easy to solve.